let's go through some details on the exercise 4, which is actually a continuing the way you what you got on your previous exercise. So on previous exercise you actually have this greenish colored components already there. You have analog sensor LM35, the analog temperature sensor, and then there's a PSoC which has the A to D converter and WART. And WART pins are actually connected to your WART bridge, which is on the kit proc, and then you can communicate with the PC. And the software actually has already some terminal control over when to send data. And okay, so you will be using a working exercise 3 as a template. If you didn't if you get stuck somehow on the exercise 3, you can still work on this exercise. Ask one of your fellow students to give you the code or the project, to share the project, the project of the exercise 3 as long as it's working, and then basically just give a credit to whoever was helping you. It's not out of your points, it's actually just some extra to your fellow students' point. Sharing is caring, so share things, it's good for the world. Okay, name the project, and then actually there are these two parts. I recommend you adding these SPI and I2C devices separately. And in here I have actually instructions to connect first the SPI. Well, that's only because in the history it has proven to be more straightforward exercise, and the students have spent some more time on this I2C bus than SPI bus. SPI bus is overall it's a straightforward in any case. It doesn't have any addressing, it just have this the chip select line, and as long as you are following the protocol, then basically it's almost sure shot that you get it working with a quite small effort. Okay, but our SPI device is a SPI A to D converter, 12 bits, but this is successive approximation kind of the analog to digital converter, which means it has excellent linearity and also excellent the accuracy. So not much bits for the say modern equipment, but modern A to D converter, but it's accurate bits. That's what counts on the making measurements. For this exercise, actually, we will be using external voltage reference for it. The easiest way would be to actually hook this power supply pin to voltage reference, but power supply pin has always some fluctuations, especially when you're powering up anything from USB. That's really noisy power what you get from there. Tolerances are so high for the power on the USB bus, so that's why you get a lot of fluctuations there. Okay, but we're using this external voltage reference MCP 1541, which gives 4.096 volts output. Okay, it sounds like it's to the power of 12 millivolts. And actually, when you hook this one into the voltage reference pin of this A to D converter, then you have very simple conversion from input voltage to the millivolts. So basically, it's 1 bit is 1 millivolt. Okay, other connections: ground. VSS is ground. Then we have differential input. Actually, this can be only a positive, so the in plus must be higher than in minus. But in any case, it can be using a differential signal. But in this application, you can actually hook this directly to VSS. In practically, you could also hook the in plus to that analog sensor output, and in minus to the ground terminal of the analog sensor. That might actually reduce a little bit of the noise. Okay, so that's the analog part and the power part. Then we have the SPI signals. So clock is the serial clock on SPI bus. D out is of course the digital output for this device, which is MISO, M-I-S-O, master in slave out signal on the SPI bus. Then there's the chip select, low active chip select, which also is, well, shut down. As you can see, this the standby current is very low. It's only 2 microamps maximum standby current, which is not much. Okay, other things you need to actually take into account is that the sample rate can be up to 100 kilosamples per second, meaning that then you are running the clock at 1.6 megahertz. You don't want to have this one running very low frequency clocks, since it's the type of the this device is a successive approximation, which means that you need to do the conversion quite fast. Okay, so that's the SPI part. You would be using the LM35 analog sensor, what you already have hooked on the PSoC. So you actually take another wire and take the analog sensor output to the SPI A to D converter. Okay, there are some more information about this device here. Okay, specifications which are quite informative. But how to proceed? Well, actually, for this device, you would need to use an external board. A prototyping board like that, or half the size, depending what kind of things you have. Half of this would be just enough for this course exercises. Okay, so you would do the connections, clear connections with the short wires, preferably short wires, and then read the SPI master component datasheet. When you add that component to your design, read the datasheet. It has lots of good information on it. So on on this PSoC creator. Actually, take a look at the, oh, that's SPI. You see, sorry, SPI master datasheet. Okay, SPI master datasheet. There we go. Okay, so basic features: 3 to 16-bit data. Okay, serial clock. It's okay. That's just fine. Then you need to run this here, a clock from some place. Then if you want to use interrupts or not, yeah, it's up to you. Okay, but anyways, then there's application programming interface, of course. But with it also actually shows you multiple devices, so slave select on multiple devices. The slave selects, you can do it by firmware, or actually have a demultiplexed firmware, so chip select signal, and then you have a control register to point one of those lines, and actually that's how you would be controlling up to 4 devices. You can actually also run this chip select line as just a digital output pin. No, nobody denies that. You just need to set it on before you call to the SPI master this API, and then you need to turn it off when the transfer is over. But anyways, for this exercise, it's just okay to use a very standard design. One note about the functions, especially on the read. Okay, read, let's see, read data. Returns the next byte word of received data available in the receive buffer. Receive buffer is actually filled during the write. When you access this this bus by writing there. Okay, so yeah, that's how you would be working on it. You basically call the write transmit data, then you wait for that component to finish by either polling this if when this component has done whatever it should be doing, and then basically it should, or then on the status register it says that there is some data on the receive, and then so read receive status, and when there's something to read, then you would read it. Okay, if you just write and immediately read, then basically it takes some time for the data transmission. The data transmission hasn't even started when you are reading the data out from the buffer. Okay, so practically that's the SPI part. And then yes, use these ports. Connect these port pins to the digital interface of the HUD converter. Okay, Then the second part, which is I2C sensor, which is just I2 on the I2C bus. Some hints on using that one. Okay, you need to also there read the I2C component datasheet, and then port 12.0 or 12.1 on this order. And remember to also put the pull-up resistor there. The electric connections are quite simple. There are not too many pins. Okay, so there's serial data and serial clock signal. Then there's the ground and, well, okay, maybe we should actually look it here. So we have the power supply, ground, serial clock, serial data, and how you connect any I2C bus things. Okay, I think we can skip that one. Let's see it from here. Okay, I2C datasheet. That's okay. Yeah, I do remember that one. Okay, Philips actually. The company which used to be Philips is now NXP. Okay, so the component has serial data and serial clock and supports standard rates of 100, 400 and 1000 kilobits per second. I think this was a slow device what we have there, the TC74, but you can read the datasheet and see if it was or not. And practically you need to pull up resistors, and actually I'm recommending 4.7 kilo. Anything between 2 and 10 kilo actually works. It's just not just critical. Without the pull-up resistor it does not work, that's guaranteed though. Yeah, and again there are some options, of course. Okay, you can define this as either slave or master. In this case you will be actually using this as a master, of course, and then practically you can configure this one to have that correct clock rate. Okay, you really don't necessarily need these clocks or reset signals unless you want to save the I2C for some other devices. We have in any case this fixed function I2C device inside. It's up to you which one to use, as long as you use master. And the component parameters actually are quite simple. Basically you just need to set the data rate as the same as for the device. By the way, since this is synchronous bus, fast device can also operate on slow bus. Okay, and yes, that's how you configure it. And then the application programming interface is here. Okay, now reminder from the previous. Let's take a closer look at this not there. They're actually in here. The datasheet. Protocol. How to access this I2C device. How to read the data. Let's see if we can find it. Okay, read this carefully. So, write byte format is there. It's standard. Actually, it's it's the address of the device with the write bit. This one is given by the device, and then one command selects which register you are writing to, and then the other command, or that's actually the payload for the so if you are accessing a register to write something there, for example, okay, I think, let's see, it has some selection of options there on this device, but anyways, if you write there something, it's a command and then followed by the data. So 2 bytes. Read byte format, you set the slave address, first write the command that select the register you are reading from. Okay. First you select the register where you are reading from, and then you do the restart. Okay, start again the USB bus as I explained on this theory part, and then again the same device address as a read mode, and then the next one would be reading the data single byte with not acknowledgement at the end. Okay, if you just read any data, meaning that basically the device already had the register pointing, then you just read it directly from the device. But there are some different registers on the device, so you need to make sure first that you are reading from the right register. Okay, yeah. So you need to do some reading of the datasheet, both this one and also the I2C master datasheet to match the device and this PSoC program. Actually, same thing, some details about the SPI while I'm at it. Okay, so there we have that one, and then I had SPI device. The protocol here. This is 12-bit. How the bits are actually set there. Remember, there's no guarantee that of anything, or actually the SPI is very vague standard. Nothing like any Deutsche industry standards. So practically SPI, this is leading edge. The leading edge signal, so it's mode 0 of that SPI bus. Okay, but then there's one bit, the first bit, the second bit, the data output is still on high Z, meaning that the device is now starting to sample. Third bit what you are getting is a null bit, so that should be 0. And the first valid bit would be most significant bit. Okay, remember you can actually have either most significant bit or least significant bit first on this SPI. This is MSB first, and then followed by the other ones. So there are 1, 2, 3 bits that you should scrap, and then read following 12 bits. So that would be 15 bits. Interesting. So actually there are 15 valid bits. Fortunately, this device actually is 3 to 16 bits. You can also select here 15 bits data width. And okay, most significant bit first, and then you need to only take the first nibble of that 16-bit word. The highest nibble, you just max that out. That's garbage, since you do not exactly know if this high Z actually will be read as ones or zeros. So these bits are in any case just garbage. Okay, there we go. So those are the hints for the exercise 4. And then actually it just follows the previous exercise, which actually send these JSON format messages. Okay, you have a couple of more data on the JSON message. So you just add 2 more fields there. You can name the fields as you wish, but they should be also temperatures in Celsius degrees. Okay, good. And that's all for the exercise. The return is the same as previously, and the deadline is May 4, 2020. Or, well, I will take a look at the deadlines at some point. I might actually change them.